Stanford. Okay, so it's recorded now. So it has been a while actually for me to come to Stanford to give talk. So it's nice that I can do that even virtually. So actually, so what I'm going to talk about today is actually summarized in this title. So I'm going to talk about what string theory would do near the photon sphere or black hole. And so this actually is my work in collaboration with Matthew Doderson, and he did much of the work in this work in progress. And fortunately, he is here, right here, so he can correct me if I make any mistake or keep me honest about it. And so I've been very interested in actually his work back when he was in Stanford with Eva and others on stringy effect near the horizon of black hole. So I'm very happy that I can do some work with him. And then, so it's an interesting question to ask whether there is any signature of string theory coming from near the black hole when the black hole is large, much larger than string scale. And if there is one, then it's interesting. We might be able to find one. And so I would like to show you that actually there is one. And so this happens even for a very weakly curved space near the photon sphere of black hole. And so I will mostly talk about the case where black hole is in asymptotically anti-theta space, because that is a case when we can compare with what we know about conformal field theory. But toward the end, I will also talk about black hole in asymptotically flat space, and then see we'll find similar effects there. Although there are some qualitative difference between flat space case and asymptotically Dojita space case, anti-Dojita space case. And so I will discuss that towards the end. So if you are interested in asymptotically flat space, please wait until towards the end of this talk. Okay, so let me get started. So once again, this is my work in progress with Matthew Doderson, who is also here. So, so what I would like to do is to talk about the correlation function, physical observable, in particular the correlation function of CFT operator, which are dual to correlation function in anti-theta space. And I consider the case of, so I got confused, I'm sorry, because I skipped one slide, I guess. Yes, so this is better. So, so let me actually do this so that I won't make the same mistake. So let's see if this works. Oops. Oh yeah, this works better. Yeah. So I'm sorry. So so I consider the in particular the 2-point function in the asymptotically anti-theta Schwarzschild geometry, which is dual to conformal field theory at finite temperature. And if you take consider the situation when n is large and two-foot coupling is large, where we expect point-particle approximation to be varied, then to the leading order, you can approximate this 2-point function by Green function connecting x1 and x2. And it is the general fact about the Green function in Lorentzian signature space that when these 2 points are connected by null geodesics, there is a singularity. So you can go back to some early study of a singularity of Green functions. Courant-Hilbert has some discussion on it. And there is a general theory of Adamar functions, things like that. So we would expect that there are some null singularity when there is a null geodesics connecting between these 2 points. So you can ask, well, what kind of null geodesics that you can have to connect these 2 points? So to parameterize things, since the boundary is a sphere, you can parameterize the relative position between these 2 points by the time difference. So we are considering Lorentzian signature space-time. So time difference, and also the angle of the large circle connecting these 2 points. So that's phi. Okay. So obviously, when time, so I normalize things so that when time is equal to plus or minus phi more 2 pi, these 2 points are like separated on the boundary. So that means that at least there is a null geodesic going around the boundary. And so you'd expect this kind of singularity. So this is not very surprising. But you can ask, well, are there other geodesics that instead of going along the boundary that cut through the bulk? Okay. So it's relatively easy to show that when the relative angle between these points is less than pi, then in fact there is a unique geodesic, and that is a one that goes along the boundary. So therefore, you only have this kind of singularity. Well, there is some kind of absolute value here, but that is the case on this side. This is on this side. Okay. But something new happens when this point goes to this side, namely that when time exceeds pi. So in that case, actually, you can find a new family of null geodesics that sort of cuts through the bulk. And so this kind of geodesics was actually discussed earlier in 2006 by Hubner, Liu, and Rangamani. And these are called bulk cone singularity. So they studied some class of shortcut like that in this paper. There is a difference between what they concluded and what I'm going to tell you, which is that they pointed out that because of this, there are some new kind of singularity for correlation function of CFT at finite temperature and other excited state. So I would like to tell you that in fact, these singularities are resolved by Stringy effect in the bulk. Okay, so that's what I'm going to tell you. So anyway, so you have this kind of shortcut in the bulk. So things get interesting when actually the time difference between the two becomes large. So in that case, the null geodesic can start winding around the black hole. But null geodesic cannot go inside of the photon sphere, because the definition of the photon sphere is that there is this stable orbit going around circular motion. And so if you are inside of it, if you come from inside of it, and then you cannot go outside of the photon sphere by the definition of photon sphere. So what's going to happen is that when T becomes large, then you can have a geodesic going around the black hole, and eventually approaches the photon sphere and stays there for a long time, and then come out. So that's what happens. So therefore, approximately when the time difference is large, the null geodesic hit the boundary at a place when the angle is equal to V gamma times T, where this is mod 2 pi, and V gamma is the effective speed of light at the photon sphere. And in the case of a 5-dimensional anti-Tidal black hole, this is a formula for that.
Hiroshi, are you considering rotation at all, or no?
Yeah. So for this work, I'm only going to talk about the Schwarzschild black hole. The rotating case is very interesting, and in fact, this is something that. So actually, if you go to the last slide, I'm going to announce that we are currently working on the rotating case, because in that case, photon sphere approaches the horizon. So that would be an interesting situation.
Yeah. Actually, we should talk, because a couple of us here also have some calculations on that, and it would be great to compare notes.
Wow, that's nice. So actually, it'd be nice either after this seminar or maybe some other time we can set up time to discuss that too.
Yeah, that would be fantastic. I think it's just the 4 of us doing this, so I think it could be useful.
Yeah. We have some preliminary thing, but we are currently just trying to finish the Schwarzschild case. And we looked at the charged case and the rotating case, and both are interesting, but rotating case is interesting because of that. So
yeah. Well, they come. All the things come together in the coordinates. Although there's a proper distance that separates them still in the extremal limit. But in any case, it'll be great to talk about that. But my question for you today was just that. Are you doing Schwarzschild here? And I guess you are.
Yeah. So today I'm just going to tell you about Schwarzschild result.
Great. Okay. Thanks.
So we have some work in progress about the rotating case. Yes. So anyway, so this is the formula for the effective speed of light near the photon sphere in ADS, and you see this is greater than 1. So the photon actually travel faster than speed of light, and of course that doesn't contradict with the causality, because what's going to happen is that this new branch of null geodesic shows up when theta is greater than t is greater than pi, so it goes like that. It looks like straight line, but it's actually a little bit curved here. This is a straight light cone. And you see that even though it looks like it's outside of the light cone here, but it's actually 2 pi identified. There's a horizontal directions 2 pi identified. So this place is actually the same as this place. So in fact, it's faster going this way than going this way, right? So namely that, for example, in this case, this is faster, but going boundary in this way is even faster. So even though the speed of light is faster than 1 near the photon sphere, but it doesn't contradict with causality. Okay, in fact, there are even more geodesics. So this is not only one, there are even more geodesics. So for example, you can have a geodesic where it starts from a point on the boundary. These are null geodesics, and end over here, but then bounce at the boundary and go this way. So like that. So you can have a new type of geodesic like that. And but you have to conserve energy and angular momentum, because here I'm considering Schwarzschild black hole. So you have a rotation symmetry as well as time translation symmetry. So this turns out that this requires that the winding number must be the same for the first segment and the second segment. Okay, so you have this additional branch. So if you add that, you have this additional branch of null geodesics. So for example, therefore, if, for example, theta is between 2 pi and 3 pi, there are like these 3 null geodesics connecting, and then if theta is greater than 3 pi, there are 4, like that. So or if you look at the time axis, it's like that. So in addition to the ordinary null geodesic on the boundary you would expect, you have these additional null geodesics. So if you fold this thing by 2 pi, then it looks like that. So of course, all these red lines are now inside of this light cone. But you have this extra singularity for correlation function. So it's interesting, but is this a prediction of strongly coupled CFT coming from the holographic description? Or is this actually resolved by Stringy or quantum gravity effect? And you can actually check to see in the calculable case whether those singularity exist or not. And you find that in the case of free conformal theory, where you can calculate things, or in the case of 2D rational CFT, those singularity along the red line do not exist. So they should be resolved by stringy effect. Yes.
So what role does the fact that the photon sphere is unstable play in the sense that you know, that's where the quasi-normal modes come from, right?
Oh, okay. So that I think would be 1/n effect probably. So yeah. Here I will be talking about G square n effect. And so actually the rest of the talk is mostly first quantized the string theory. It only happens on the single string worldsheet. There could be other effect that we have not taken into account. But we'll see that this effect is going to resolve the singularity.
Well, I mean, of course, the quasi-normal modes are classical, but maybe, I mean, I would have to think about my question a bit more, but. Yeah,
so one thing that might happen could be that if this string traverse near the photon sphere, it could excite some of these quasi-normal modes. Is that the kind of things you might consider?
Yeah, I mean, yeah.
Yeah, so that would be one of n effect which we have not considered. But yes, that might be additional thing. But we are going to see that this stringy effect is going to be enhanced near the null geodesics. So
sorry, question.
Yes, please.
Sorry, I'm a bit confused. If you have, isn't it the case that there will be no geodesics in the bulk that will always hug the boundary?
In the pure ADS, yes. In pure ADS, yes. In the pure ADS, all the interesting null geodesics are on the boundary.
So this is, this happens when you have
non-trivial
black hole.
Yeah. So yeah, so in this case, it might have to do with the fact that ADS is both rich flat, is both Einstein and it might be special feature of ADS, pure ADS.
Yeah, it's just hard to believe because asymptotically, all of them would look like vacuum ADS. And
now I'm going to show you the explicit construction of this.
Okay. Yeah, sure. Sorry, go ahead.
Yeah, but I think you are thinking about pure ADS, I think.
Yeah.
Okay. So in fact, there are cases when this type of similar singularity associated to null geodesics get resolved by stringy effect. And this is something that I worked with Matthew last year, inspired by an early work by Juan Maldacena, David Simmons-Duffin, and Sasha Zhivoedov. And this is again resolution of singularity from null geodesic by stringy effect. And in fact, this work was meant to be an exercise before we work on this situation in the black hole. And so what we did was that these three people, Juan and David and Sasha, pointed out that if you consider correlation function, now this is a pure ADS case. Then in this case, you can have a situation where you have correlation function of several points on the boundary, and they can meet, the null geodesic emanating from them can meet at a point in the bulk. And if that happens, these correlation functions can have singularities if you calculate it in a point particle limit. But in CFT, you don't expect such singularity in generically. So again, this has to be resolved. And so there was some preliminary discussion on how this can be resolved in this paper, and Matthew and I quantified it. And so what we found is that it's actually nice to use the Mellin transform of this correlation function that developed by Penedones, and which relate CFT correlation function to S matrix in the bulk. And then you find that when these lines approaches null geodesics, then correspondingly you have to use high energy S matrix to evaluate the effect via the bulk point. And since we are considering high energy fixed angle scattering, you can use the analysis of Gross-Mende. And Gross-Mende shows that if you consider S matrix of high energy and fixed angle, the worldsheet start expanding. And you get a much sort of milder ultraviolet property. And we show that that effect resolves the singularity here. So there is already a precedent that the surprising null singularity that are predicted in the point particle limit can get resolved by stringy effect. In this case, Gross-Mende effect. So today I will show you that now there is another type of null singularity. Null singularity due to the curvature, due to the existence of black hole. As it was pointed out, asked somebody earlier, this is not something you expect in pure ADS, but this happens because of the black hole. And it turns out that this effect is not resolved by Gross-Mende effect, but it's resolved something else. And that something else is due to tidal force of black hole. And tidal force generate a worldsheet particle production, and that resolves the singularity. And this effect gets enhanced when the geodesic approaches null. And so this is what I would like to show you. So here is some. Yes?
So, sorry, I have one more stupid question.
Yeah, please go ahead.
If you, even if for like thermal CFTs, if you take the 1+1 D case where it's just a cylinder, then aren't there singularities on the boundary too, because you can wind around the thermal circle and
There
there
are
will be
singularity on the boundary too. So these are blue ones. Am I understanding the question correctly?
oh, so yeah, sorry. Okay, good. Yeah, thank you.
There are singularities. So these are singularity you expect and exist. For example, in these cases, these singularity along the blue ones exist. And then we find that the red one don't exist.
Good, thank you.
Okay. Okay, so here is analysis of geodesic in ADS-Schwarzschild geometry. So you have time translation invariance and rotation invariance. So you have energy and angular momentum conserved. And so then geodesic equation becomes this kind of classical Newtonian program with this potential where L and E are conserved charges, conserved quantities. And null geodesics are obtained by taking the limit of both E and L large with a ratio fixed. And in fact, it's nice way, there is a nice way to see it. So for example, suppose you have two boundary points with relative time T naught and relative angle phi naught. And suppose that these are connected by null geodesic. Okay. And then suppose there is a neighboring points that are connected by space-like geodesics, and let's denote it by T and phi. And then you can show that these are actually related to each other by this relation. So you can see that as E and L goes to large, then T and phi goes to T naught and phi naught, and now there is a null geodesic connecting them. So that's what I mean by null geodesic is obtained by taking L and D goes to infinity with a ratio fixed. Okay. And in fact, yeah. There is also a nice formula you can derive, which is the following. So suppose, for example, you start from the point x1, and then wind around, and then come back to x2. Okay. And then as I said, there is a null geodesic connecting between them when phi is approximately equal to v gamma times t, where v gamma is a speed of light near the photon sphere. So you can see that as phi approaches v gamma to t, energy is given by this formula, and in fact it goes to infinity, and L also goes to infinity. So this actually is a useful formula that I'm going to use. But okay. So I hope everything is clear so far. People are already doing it, but you are welcome to ask a question anytime, okay?
Can I ask a question?
Yes, please.
So it's about your analogy with the bulk point singularity.
Oh, yeah. Okay.
So I'm a bit confused about the analogy because I thought that singularity is something that shows up only in the limit of flat space when I take the flat space limit. So at any finite curvature is not a true singularity, but in the limit it arises.
Oh, I thought that this is a singularity that appears in the large n and large two-foot coupling. Am I mistaken?
Yeah, well, that wouldn't it? I guess wouldn't it be equivalent to going to the flat space limit?
No. Well, that would be a different limit, I would think. These are singularity for correlation function of CFT in that limit. Okay. And this is a singularity that you obtain in correlation function in anti-theta space in the point particle limit. So these are the same kind of, this shows up exactly in the same kind of limit as this case. So this is also large n, large two-foot coupling.
And large energy too, I think.
Well, this is about conformal field theory, large n, large two-foot coupling, and singularity appears when 2 points are separated by null geodesic, which, if you look at the geodesic, correspond to the large energy, large angular momentum limit.
Yeah,
but
and that's what also gives you the flat space limit.
This is the singularity that appears for large and large two-foot coupling CFT, which is also the case here. So that's what I meant by analogy.
Yeah.
That's clear, or do you have more questions?
Yeah, I guess I was a bit confused because you at the beginning you said that there is a qualitative difference when you go to the flatter space.
Yes, yeah. So maybe
while there, I thought there is actually in that case there was no qualitative difference. It was exactly the fact that I'm going to get the S matrix with the delta function. Well, in flatter space, that was the source of the singularity also in ADS.
Maybe you can wait until I tell you about what I meant by difference with the flat space limit. I haven't told you what happens in the flat space limit.
Okay.
I will tell you at the end. And then we can talk about that. That sounds reasonable?
Yes, thanks.
Okay. So anyway, so here it's a difference. This is this bulk point singularity in multi-point correlation function, and this null singularity for thermal correlation functions are both for large n and large surface coupling. Both happens in null due to null geodesic going through the bulk, and but the resolutions are different. So in this case, resolutions are due to Gross-Mende effect, and I'm going to tell you that the resolution in our case is by a tidal effect. Okay. So I'm telling you about kinematics of null geodesics in black hole, ADS black hole. So as I said, so in this case, the energy and angular momentum tensor angular momentum diverges. So that's sort of a signal for going to the null geodesics. Okay. So you can see how you can actually reproduce the null singularity by doing this simple calculation. So you see that in the, suppose, so let's consider the simplest case when the mass of the particle is large. So in this case, you can see, you expect a 2-point function is given by the simple formula of exponential of mass times geodesic length. So exponent is a positive quantity. So how can it diverge, right? So you can ask, well, how can you get singularity? And there is actually a nice way to get singularity. So this is a formula for the geodesic distance between the 2 points. So you go to the a black hole and goes around and come back out. So then there is a reflection point R plus, which is a distance, shortest distance from the black hole. So you start from some UV cutoff surface and then go near the black hole, going around and around. I need to actually see my own picture to see if I'm doing it correctly. And then going back out to the boundary, right? And then so you approaches and going back out, so you have a factor of 2 here. So I'm just integrating this formula. Okay, so I'm just integrating this formula. Okay, so then when E and L is large, actually this geodesic distance is given by this formula, the ratio, log of ratio of UEV minus E square minus L square. So, but this LUV dependence gets renormalized because you have to rescale the 2-point function by getting rid of this. And then you are left with this one. And then by using the previous formula here, you can relate it to this singularity. So voila, you get the divergence, you get the singularity when phi becomes V gamma T. So this is how you find this singularity. Okay, so I want to show you how this singularity gets resolved. So I would like to argue that this is caused by tidal effect near the black hole. So I'd like to evaluate what kind of tidal effect that string worldsheet experience as you go through this geometry. So you send this from the boundary, going near the photon sphere and come back out. And then it's going to get some squashed and expanded. And what kind of effect? So there is actually a nice formalism developed by Merck. And so that makes use of this tidal tensor, which is a component of Riemann curvature. And so I'm going to use U as coordinate along the geodesic. And then here I'm considering ADS5. So there are 3 transverse directions. And so I'm going to use also normal tetrad. And this nice paper by Mark actually explains for us how you can calculate also normal tetrad parallel transported along the geodesics. So you can actually use this to calculate the tidal tensor. Okay, so this formalism is nice because then you can, so this expression allows you this allows you to rewrite the metric near the geodesics in this way. So for any geodesic, for any given geodesic, you can calculate this tidal tensor by calculating the parallel transported tetrad. And then you can show that metric can be expanded in this way. Okay? So this is very much like Penrose limit, except that this works for any geodesic, not just null geodesics. So then the tidal tensor in the case of ADA Schur series black hole is given by this formula where L is going to become large when you approach the null geodesic. And so here I'm writing unstable and stable because if you, for example, truncate this metric to the order of x squared, then the worldsheet theory is just harmonic oscillator, just like in Penrose limit string theory. And in that case, there is one direction of string worldsheet which is unstable with upside down harmonic oscillator potential. And then there are two directions which are stable. So these correspond to like these directions and these directions. So there is one direction. So when the string travels in this near the black hole, there is one direction which tries to stretch the string, and then there are two directions where the curvature tries to squash the string. And interestingly, this effect gets enhanced as E and L becomes large. So that means that as geodesic tend to null, the tidal tensor grows like L squared. So that means that if as string travels near the black hole, you get big tidal effect, and that's going to squash and pulls and squash the string worldsheet, and that causes a large number of particle production. Now, so this actually suppresses the amplitude two-point correlation function for the following reason. So the way that you calculate is that you start with you send a particular stringy state from the boundary to the boundary.
So Hiroshi, sorry, can I ask a question about your previous state? So I mean, this is very interesting. I'm just curious though how long this approximation lasts, because as the string gets excited, it's producing modes, and those the size of an ordinary string in one of its stationary states grows like the square root of the mass or whatever it is, or sorry, I forget the sorry, it grows like it occupies a region of order the square root of its own total length, I should say. So anyway, it's getting bigger. So, but it's still being modeled as this thing that's moving on a null geodesic. And how does that ever break down, that description of it?
Well, I think that is a string. So I'm assuming that there is a order of sizes. That I'm assuming that the string size is smaller than Houghton sphere size, which is smaller than ADS size.
Yeah. So the square root helps you. I mean, it's not the string length per se, but it's the square root, I guess, that helps you.
Okay. Yeah. I think so. We can see how much strong the effect is going to be, and then maybe I will write a formula for the suppression to kick in, and then we can convert that into question later. So can I do that after we get there? So because I'm going to write for you the formula where how strong the suppression is. The question is that could that effect kicks in before other things that you're worried about start happening, right? So anyway, so the kind of things that I wanted to say was that suppose you have this string which is going near null geodesic, and then so you look at it and you approach the null geodesic, and then the tidal tensor becomes large, and the string gets stretched. And then what happens is that you send a particular stringy state, and then how it goes around, and then in the end, you are calculating two-point function. So you're calculating the amplitude where a string ends up with the same state. So you need to start with a particular string state psi, send that around the black hole, and then you want to calculate the amplitude where it end up with the same state psi, right? So that's what you are calculating. But if the string worldsheet starts producing lots of worldsheet excitations, then the probability, the amplitude of ending up with the same state becomes small. So that can suppress the amplitude, and so therefore that can compete with the divergence that can come from the null singularity. And so that's what I would like to show. Okay, and in fact, therefore, I'd like to describe the calculation explicitly, where we can calculate the Bogoliubov coefficient for the particle production or stringy excitation on the worldsheet caused by this tidal effect, and then calculate the vacuum to vacuum amplitude and see how that's suppressed by this effect.
All right, let me ask one more question about the setup.
Yes.
So this is a 2-point function. So there's a source at the boundary that is very localized, right?
Yes.
So that's the thing that's kind of sending the string in, but the string.
Yeah, but since the source is at the boundary, so it actually can be excited string state because everything goes to a point on the boundary by scaling factor.
Okay, I mean, I mean, abstractly in the 2-point function, that could happen. Of course, a massive object just bounces around in the bulk; it never gets to the boundary at finite energy. But that wasn't actually my question. My question was, although now that you say it, I have that question. So sorry.
Yeah, but here I'm considering space-like geodesic.
Yeah. Okay.
It goes to the boundary.
So fine. But then you're doing a Lorentzian calculation of the excitation of the world, which is a very physical picture of what's going on. So I'm trying to understand the connection between the sourcing at the boundary in this point-like way and the traditional first quantized string state, which is not anywhere near that configuration.
Why do you say that? Even though the source is a point on the boundary, but it can source excited string states.
Well, if it's localized, it takes some time for the string to spread out the way it would be as measured by its variance and all of that in the ordinary string states. We don't need to belabor this right now. I suspect Matthew knows what I'm asking because we considered that in the past, but we don't have to go there now. But it's a question that I have. I guess your comment made me think more about the question though of if the string is getting excited as a Lorentzian thing, it would just bounce around. It would never get back to the boundary. No,
that's not what I meant. So even though you start with a particular string state, you go near the photon sphere, near the black hole, get excited, and it becomes superposition of various different stringy states. And they all try to go to the boundary. And they can go to boundary because we are slightly space-like geodesic. And you can go to boundary. And but majority of them are not the original states. So therefore, the 2-point function.
Aren't these excited states are just different operators, slightly longer operators, right? I guess.
Yeah. So therefore, if you are calculating off-diagonal element, you can correct those. But we are calculating diagonal element. So does that make sense, Sean?
Yes, absolutely. Yeah.
Okay. So so suppression happens because we are calculating the diagonal element when there is a large number of excitation going on. So I'm going to show you explicit calculation of this. And it's actually simpler to do that in Penrose limit. We can do that in the full tidal tensor formalism, but for the purpose of, so I only have 20 minutes. So let me show the calculation in the Penrose limit. So just briefly, so this formula is true for any along any geodesics where phi is a tidal tensor and expanded to the quadratic order. And but a Penrose limit is a limit when this geodesic turned out to be null. So in that case, L is infinite and etc. So if you do that, then you have various interesting things happens. For example, if you have Einstein manifold satisfying Einstein equation, it becomes rich flat manifolds in the Penrose limit. So therefore, the trace of phi vanishes. If you manifold is conformally flat, it remains conformally flat. So the wild tensor vanishes. It turns out that the pure anti-theta space, this is something somebody asked earlier, is both Einstein and conformally flat. So therefore, if you take Penrose limit, you get rich flat and conformally flat metric. So that means that it's actually flat, period. So you get the Minkowski space. And so that's why the Penrose limit of pure ADS is trivial. On the other hand, the kind of things that is interesting is that when you have a space which is ADS times some compact space, then if the null geodesic is going in the compact direction, you can have non-trivial Penrose limit, and then you get plane wave and PP wave, and there are lots of interesting stuff. In the case when we are interested in, we are looking at the ADS Schwarzschild. So in that case, the limit is very simple. The original tidal tensor was like that. So you're taking L goes to large, so we're just dropping this one. Okay. So in the Penrose limit, therefore, the worldsheet equation motion is just this harmonic oscillator with time-dependent potential. And so this is one direction, x1 direction, which is unstable. So that's why you have upside down potential. Well, when L is very large, then for sufficiently small n, this is unstable. So that means that you start exciting lots of stringy states, stringy excitation for some string mode, right? So when p times L is very large, there are lots of instability mode, and that gets interesting. So we can actually analytically find estimate of tidal effect in two different limits. And one is a limit when the relative angle between these 2 points are barely larger than pi, slightly larger than pi. In that case, actually, you can show that you can actually approximate this time-dependent potential frequency for the harmonic oscillator by delta function. So you can use a sudden interaction approximation. So this is the same for 2 and 3 directions. The difference is that 1 direction is unstable, so you have plus sign here. 2 and 3 directions are unstable, so stable, so you have minus sign. So when t is slightly larger than pi, then you can use sudden interaction approximation. So what you do is that suppose interaction takes place at tau equals 0. Tau is the worldsheet time. Then before the interaction kicks in, you have this harmonic oscillator oscillating happily. And then you kick it by the sudden interaction, and then it becomes a different superposition of the same harmonic oscillator. But because it's kicked by this potential, so A and B, the A and A dagger become a superposition of B and B dagger, and they mixed up like that. So this is a unitary matrix. There is an I here, and given by these parameters. So this N is a mode number. Okay, and so then you can see. So this is a Bogoliubov coefficient, and then vacuum to vacuum amplitude. Namely, suppose you start from the vacuum state. Can be some excited state, but let's just for simplicity consider vacuum state. So you start with vacuum state, and what's the amplitude of that ending over here? So it's a vacuum to vacuum amplitude. So for each mode, what you have is basically the 1 over square root of this coefficient, this diagonal coefficient. And you are supposed to take a product of this for all positive n. And the product of this kind of things for all positive integer n is a gamma function. So therefore, the vacuum to vacuum amplitude is given by this gamma function. So this Bogoliubov coefficient calculation shows that the vacuum to vacuum amplitude is given by this. And then you take the large L limit, and you see that there is a minus sign, and then you have this. And then so you see that indeed it's exponentially suppressed for large L. So this is what we wanted to see. So you see that when the geodesic approaches to null, then there is a large tidal effect, and this suppresses the vacuum to vacuum amplitude. And so this is the amplitude for stringy excitation. Of course, you have to combine that with a 0 mode piece. And so if you combine that and then the Fourier transform back in P minus coordinate, you find that the 2-point function is actually not divergent, but finite at phi is equal to V gamma times T. Or this is when T is slightly larger than pi, actually. So maybe I might have skipped one slide. Maybe, no, I did not. Okay, good. So if, yes?
I ask about how did this depend or not depend on how many circuits you did of the photon sphere?
Yeah, so here I'm doing the opposite limit. where I'm not going near the photon sphere. So this happens even when you are actually far from photon sphere. It happens whenever you have even slight curvature, turns out. That it's actually, it does not happen in pure ADS, but because Penrose limit is trivial. But in the pure ADS, as somebody said, there is no interesting bulk geodesic. So it's consistent. In all other cases, you have interesting Penrose limit. And whenever you have an interesting Penrose limit, you have this divergent factor. Usually when you talk about Penrose limit, you drop this factor. But in fact, there is this factor there. And this gives you a large tidal effect. And so this suppresses this amplitude. So this is actually the situation where 2 point is actually just barely greater than pi. So this is when you start seeing this a new branch of null geodesic, and that is actually immediately removed by this effect. You can also ask what happens when you approach it. So behavior is a bit different. So that's interesting. So when you approach it, when you have when now that you can consider opposite limit when the time before I get there, I forgot I wanted to say one more thing. So previously this was infinite. Previously it was like 1 over phi minus v gamma t raised to the power of 2 delta. So this was divergent, but now it's finite. And but it's finite, but you have L string length. So up to here, I was writing L string to be 1, but I'm restoring it. So if I restore L string, it's 1 over L string to the cube. So if you take the limit when string length goes to 0, then it diverges back. Okay? So that's what happens. You can ask the situation that Eva was asking about, which is that now the the time difference is very large, so that the null geodesic go wound around photon sphere many times. Okay, so in that case, actually, you can take a different limit because when a string goes near the photon sphere, it stays approximately around the same place. So the potential actually does not change very much in that. The only change happens is that when you approach the photon sphere, and then when you go back out. Over here, the potential is changing very slowly, so you can use the adiabatic approximation. Okay, so these are all useful things you learn in undergraduate quantum mechanics. And so then in that case, you can again estimate, and so these R plus and R minus are 2 reflection points that you can solve from the geodesic equation. And then you have this. And again, you have exponential suppression for large error. So this resolves the null singularity. So in both cases, actually the null singularity is resolved. So I started with a puzzle that what's going on with these null geodesics that are not existing in cases where we can calculate thermal 2-point function. And it turns out that it's resolved by stringy effect, but stringy effect that is different from the bulk point singularity. That is by the Walsh tidal effect. Due to the enhanced tidal effect near null geodesic. So it's interesting that this seems to happen universally whenever you are close to null geodesic. Well, you can ask where it's all you can say, well, it's all interesting, but what about asymptotically flat case? Can we see something like that in the event horizon telescope, for example? So in that case, ideally you want to calculate S matrix because correlation functions are not observable. So here we're calculating 2-point function, but you can interpret it as 2-point function at Cohen, Moore, Nelson, and Polchinski. So this is their paper in 1983. So when this paper appears, I didn't know what they're doing because 2-point function in the bulk is not, I thought was not physically observable in string theory. But after mid-1990, you can interpret it as 2-point function of T-1 branes. So if you go back to look at the papers, that's what they are calculating. So anyway, so you can calculate the same thing, and you can ask what kind of singularity can you have. So in that case, you only have one branch because there is no boundary. So you only have, and there is no bouncing off the boundary either. So there is only one branch of geodesics. And so this is a kind of caricature of geodesic. Of course, I mean, it's only one branch, but it goes around, right? This is so this, you have to fold this by 2 pi, so you can have various winding around black holes also. And so since this is only one branch, so it's resolved throughout. So for small t, the resolution is small because the curvature is small from far away from black hole. But when t becomes large, then it starts going around the black hole many times, and the photon sphere, that is, and that effect gets enhanced, so you have a strong suppression. And so in some sense, this may be more interesting. So there is only one branch, and you can qualitatively see the effect of existence of photon sphere by looking at the various. So what you expect to see is that suppose you have black hole in asymptotically flat space. Suppose you calculate 2-point function. In point particle limit, the 2-point function is sum of various geodesics, and there are infinitely many singularities because you have various branches of null geodesics. But stringy effect kicks in, and some of the null singularities that accumulate to the large T start to become very soft, strongly suppressed. So namely that as T becomes large, you start seeing a strong stringy effect. Even though black hole can be large and the curvature is weak, but if you wait long enough, that effect gets accumulated and causes a strong suppression. So then you can see some strong difference between the point particle limit and the string limit in this flat space case. So anyway, so I didn't have time to talk about, and we actually are still working, which is a rotating black hole case. And Eva said that she also have some thought on that. So I'd be happy to discuss that together with Matthew, either after this or maybe some other separate time. That might be better. And but this is an interesting case because if you take extreme limit, photon sphere approaches the event horizon, so you may be able to see this kind of effect at our event. So initially we thought we can see the effect of event horizon, but because of photon sphere, at least in ADS correlation function, you cannot see that. But in the extreme black hole, extreme rotating curve ADS, you may be able to see it. Okay, so that's all I wanted to say. Thank you for your attention.
Thank you, Hiroshi, for this beautiful talk. Yeah, let's all unmute ourselves and applaud. More questions for Hiroshi?
Yeah, can I ask? So I guess, as you know, and others, there are also null singularities bouncing off the black hole singularity, right? There are null geodesics that potentially produce poles and correlation functions. I guess this mechanism would apply to those too. Is that right?
Sorry, so maybe I'm lost. What kind of situation do you have in mind?
Well, you know, you send in a geodesic that goes through the Einstein-Rosen bridge, and in a limit, where it becomes null, it can bounce off the singularity of the. Oh
yeah, that's right. Yeah, so I think that so I have to think about that situation, but that's a very interesting question because I think that from what we found this enhancement of stringy tidal effect seems to happen whenever, generically. Well, for example, there are situations where it doesn't happen, like pure ADS, where Penrose limit is trivial. But in generic situation where you have non-trivial Penrose limit, it seems like this is a ubiquitous phenomenon.
So if I could just comment on that for a second. So what Steve and friends found was that that singularity is actually already resolved by the bifurcation of 3 complex geodesics. So
no, that's a separate question. So this, where exactly the singularity lives is a bit of a subtle question, and maybe it's not understood, but that's not, I mean, there's still a saddle point. Now, whether the saddle point does anything is a different question, but that in itself doesn't resolve the singularity. It just means it's hard to find, or might not even be.
Yeah, so Your question is whether our effect could also resolve the singularity on the second branch.
If it's there, yes.
I see. Yeah, I don't know about that.
And for example, if you do the calculation in other dimensions, you don't get these branch cuts and stuff, actually.
May I ask a question?
Yes, please.
I assume that if you make a curve, let's say you rotate the angle at fixed time, at a particular place without stringy effects, you would have a divergence, as you explained.
Yes.
But still, if you have a small string scale, say compared to ADS scale, you would have a steep peak.
Yes. Yes.
Yeah.
Yes.
So what I'm wondering is, if you just think about it from the boundary point of view, and let's say that persists at large but finite n, that the 1/n effect, you still have a bump. I mean, the naive interpretation, without thinking about it at all, 2-point functions in a thermal gas in a can should just decay. And so I wonder if this represents some kind of failure of naive thermalization. And this is something that's interesting. And roughly speaking, it's because the photon doesn't ever get close to the horizon. And so that's where thermalization really happens. These kinds of failures of naive thermalization are interesting. And I mean, the extreme case is in these, I guess, what are they called? Oscillating geons that Gary and Santos and Don Maralf have studied, where you can set up a large lump of energy in ADS that has more than enough energy to make a large black hole in ADS, but it just doesn't do that classically. It just keeps oscillating forever. And they've argued that at least probably alpha prime corrections and even maybe 1/n corrections don't stop that. Non-perturbative effects in 1/n stop that. So it seems that there are examples of where a system that is thermalizing, chaotic, there are certain sets of initial conditions that don't do that as well as they should. This has been seen in many body physics. There's some in AMO and stuff, and where you can set up in a system that a lot of initial conditions thermalize, certain special conditions just keep oscillating much longer than they should. And I wonder if this bump, let's say it occurs at n=3 in QCD, you might find some surprising bump in a 2-point function that, the system doesn't thermalize just according to naive expectations. And I wonder if there's a way of thinking about what you found from interpreting it from that point of view.
That's very interesting. Of course, I mean, we are taking a finite Hood coupling, but the n is infinite.
Yeah, but you might have guessed that 1/n corrections don't completely destroy it.
Not mixing with other states. So there could be some other enhanced effect, like, for example, Eva was suggesting maybe there is some enhanced interaction with quasi-normal mode near the photon sphere. And that, that can cause
it's possible. Yes, there could well be, but I guess it's possible the bump would stay at small enough G string.
That's true, yeah.
And so I guess this bump would be surprising for a condensed matter theorist that probably expects something pretty featureless.
So is the specialness of the initial conditions that you have in mind the fact that the geodesics are chosen to be the ones that are going to get close to null? Is that what you had in mind?
Well, that they're pretty high energy, I guess. Yeah. You put a high energy probe into a hot gluon gas. You might have said, the hot gluon gas it'll split into lower and lower energy gluons, and it'll just turn into the gluon soup. This sort of says that the high energy gluon retains its form maybe longer than you expect, and could get out to the other side of the can without turning into thermalizing. So it's a feature of high energy injections into the hot gluon gas. That's true.
But it's not just high energy, it's large angular momentum. So there's something that keeps the particle from getting inside the photon sphere. And
but do you need large angular momentum for the first set of trajectories that Hirose showed? Or is that just for the wrapping multiple times around the
you need
photon
another
sphere?
drop inside the photon sphere, right? So I mean, there's some kind of sequestering going on, right? So there's some degrees of freedom that are sitting at the thermal wavelength.
Yeah.
And then the Yang-Mills theory has some other set of degrees of freedom that are describing things that are at large radius and ADS.
Yes.
And so what you're trying to do is you're trying to keep those two sets of degrees of freedom from interacting with each other.
That's right. I
And
thought the first geodesic,
large N.
but I first set the geodesic that Hirose showed that only kind of, it doesn't wrap around the photon sphere. It just goes from one side to the other. That doesn't seem like it would require asymptotically large angular momentum. But I agree with your comment that there is some sequestering going on that's a little bit surprising. And that you know, I guess the question is n equals 3 large enough n for that to already happen? And this would be a finite temperature consequence of the relatively weak interactions in QCD. The 1/n corrections, I mean. Well, that's all I wanted to ask about.
Question. Agree. Hirose, did you say what happens in ADS3 in the BTZ case?
No, so in BTZ case, actually, we don't have this effect. And there is no additional geodesic. And that's because BTZ is a quotient of pure ADS. And in pure ADS, we don't have a interesting panels limit.
But okay, you mentioned something about 2D rational CFTs not having these extra
Yeah, that's right. So this was not really a counterexample in that sense. You're quite right.
Okay.
So it is true that 2D rational CFT example is a case where we are pointing out the absence of this singularity. In the case we don't also expect in the bulk. But nevertheless, this seems to suggest some general pattern. So, but you are quite right. So in ADS3 case, we don't have this kind of bulk null singularity.
Can I ask?
Yes,
I guess it's related to the flat space limit again. So imagine I have a black hole and I want to discover the string scale using this phenomena. So what I do is that I send a wave packet and
Can I show the slide for the flat space case? Maybe we can look at that and then also. So let's see. So it should be the. Can you see?
No, I can't see it.
We only see the boundary.
Oh, so maybe I'm sharing a wrong file. I hope I'm not embarrassing myself by doing that. You don't see that?
No. Are you using a double monitor?
Oh yeah, I do. Oh yeah, maybe that's why. I apologize. So, oops. Let me organize my desktop a little bit.
There you go.
Oh, can you see?
No, I can't see.
Okay, good. All right. Yeah. So this is the situation of a symptotic flat case. Yes. So please repeat the question.
Yes. So I want to. Well, my question, I guess, is kind of qualitative. I want to try to understand how to set up an experiment to discover the string scale.
Yeah.
So I have a black hole, and I want to send a wave packet. Very carefully send a wave packet, and this wave packet I want to gradually make it more and more focused. And my understanding is that you are saying as I make this wave packet more and more focused, on the other side I keep getting a more and more focused answer until I hit the string scale, and then something unexpected happens. Now my question is that isn't there any other effect, say for instance this instability of the photon sphere that this spreads my wave packet well before getting to the string scale.
Yeah. Okay. Good. So let me answer your question. So the kind of effect we are interested in would kick in as follows. So suppose we have this 2-point function. Then suppose we put the 2-point initially in a space-like separated situation, and we move one of the points so that it try and go to the null geodesic. And then, as you said, at some distance, at some point, you start seeing stringy correction to the expectation, and that effect become more and more enhanced as you go to larger and larger t and larger phi because of the accumulation of this tidal effect. So then you can ask, well, but if you approach further, you can have other effects kicking in, such as 1/n effect, etc. We have not analyzed it, but I have some expectation based on my earlier work with Matthew in the bulk point singularity case. There you can have also ask the same question. So namely there we saw that Gross-Mende effect kicked in, but there are other effects like black hole formation. So for example, if you have 2-point function, you can form black hole and black hole evaporate. And there are also effects like Veneziano studied for high energy, the iconal approximation. And these you can estimate. And in that case, it turns out that in the setup that we are interested in, these turned out to be subleading. And yeah,
I guess my question is that if I try to approach this geodesic limit from the wave packet limit, because we are going to talk about like massless fields like graviton 2-point function. I guess I'm trying to understand if I approach it from the wave packet side and try to make the wave packet more and more narrow to becomes closer to geodesic, do I get some surprise before getting, or do I get some spreading before getting to the point particle limit?
Sorry, so maybe you're thinking about different setup of calculation. So here I'm calculating Green's function.
Mm-hmm.
So you have 2-point sources in the bulk, d-1 brane, and I'm calculating 2-point function of d-1 brane in flat space. You can consider superposition of all these guys to make wave packet, I guess.
Yeah.
Yeah, I'm not sure why you want to do that.
Well, I guess because I'm thinking about doing some experiments. So I want to send a wave of, I don't know, photons or gravitons. So I naturally produce a wave packet.
Yeah, well, of course, I mean, you can calculate S matrix. And so I think that we can start from this calculation and calculate S matrix. That would be another physical observable. So I think, I suspect that you can see the effect of this null geodesic and its resolution by looking at S matrix from this. We haven't done it, but I think it's possible.
Also, can I ask maybe slightly related question, but if you're not finished, Mehrdad, we should continue with yours.
No, I guess I'm finished. I don't have it.
Well, okay, I'm kind of trying to understand how the approach involving the particle production on the world sheet, which is a very physical, very Lorentzian effect, how you go about matching that to the thing you've been stressing, that you start from a source and moreover it's a Euclidean or a space-like 2-point function. So at some point, so you're saying there's an overlap between the two. So does that mean you're computing a superposition of these Lorentzian particle production single string state evolutions, or I'm just struggling to understand how you do the match.
Yeah, so I'm not, so I need to sort of understand precisely what you mean by physical versus mathematical. So we are entirely in the Lorentzian setup. We are calculating Lorentzian two-point function. Although for technical reason, we are considering space-like separated point. But these correlation functions are physical observable in the context.
Right, but you're doing it in the first quantized description. So you have some, and then you have some particle production effect on the string, right? Which I understand you can do in a fully. So
it's a Lorentzian effect on the worldsheet in the Lorentzian space-time.
Right. So I understand that very well when you have a string that's actually propagating in the space-time, but that's not your situation because you're talking about a space-like evolution, not just a string that's in some space-time evolving and then getting excited.
So can I try to address this maybe? So the way that it technically happens is we have a trajectory and then we have the determinant of the fluctuations around the trajectory. And that determinant is matched to the Bogoliubov coefficients.
Okay, but I guess my confusion is very basic. It's this is a space-like trajectory, right?
Space-like trajectory in Lorentzian space-time, yes.
Yeah, it's a space, right. So when you say match to the Bogoliubov coefficients, I'm not supposed to, am I or am I not supposed to think about it as, well, are you basically saying that it matches with what you would, with some calculation of particle production?
So on the string worldsheet, even along near even if you consider fluctuation around space-time space-like geodesic, you can do Lorentzian calculation on the worldsheet. You have Hamiltonian, you can consider Lorentzian time evolution on the worldsheet time, and that's what we are doing.
Okay.
And then as string evolves in Lorentzian worldsheet time in the space-like geodesic in the bulk, it starts creating worldsheet excitation, and that's what we call worldsheet particle production. And so because string travels and stretched, etc., it starts exciting lots of stringy states. And so we are calculating Bogoliubov coefficient for that excitation.
Okay, and you can do that abstractly along the space-like trajectory, I suppose.
Yeah, that's right. It's the same mathematical formalism, because from the point of view of string worldsheet person, even if the space is entirely space-like, you can still consider Lorentzian time evolution on the worldsheet, right? That's what we are doing.
Sure, yes.
Can I make a comment? So so it doesn't need to be the case that there is a classical string trajectory between the 2 points where the Green's function is being evaluated. So it's a first quantized formalism. So the strings have some wave function, which is what one's really computing by the first quantized formalism. So in calculating some quantum amplitude in the first quantized formalism, you're precisely calculating the Green's function. You're not calculating some classical string trajectory. You might be determining where the peaks of that Green's function are, looking at the classical trajectories. That doesn't mean that the full quantum amplitude of the first quantized string theories is entirely saturated by classical trajectories.
That's true. Although we wanted to estimate the largest dominant contribution to the two-point function that come from geodesics connecting.
Of course.
But are you saying, so Matthew was saying that this effect is basically a one loop determinant, is that right?
That's right. Yes.
In the Mende description, so.
It's the same as saying that we are approximating the metric to the quadratic order. So if we look at this as worldsheet sigma model, then tidal tensor expansion is the same as sort of Gaussian approximation to the worldsheet nonlinear sigma model.
Okay, and the tachyon on that, in some sense, in that space-like evolution, was the thing that was driving it to be quite a large effect. Did I have that right? That
yes, that's right. So tachyon, tachyon, not in the sense of space-like tachyon, but worldsheet tachyon.
No, I understand. Yeah.
But in some sense, actually, both excitation contribute to the suppression, because if you look at this, then you see that this square root of, can you see this? So square root of gamma function, this comes from this unstable mode. And this comes from stable mode. And there is square root because there are two stable mode and there is one unstable mode. And both of them contribute to give rise to this suppression. So in some sense, it's both sort of stretching effect and squashing effect that sort of produce lots of particle and suppress vacuum to vacuum amplitude.
Sorry, okay. But okay. And when you talk about the geodesics, you mean massive? I mean, how does the excitation, the fact that it's in some sense getting more massive, affect the geodesic itself?
So let me see which massive. I'm not sure I understand. So n is a more stringy excitation mode. So when n becomes larger and larger, you get a lot more stringy state excited, and you see that in the unstable direction there is a turnover.
Right. I just trying to understand. So the calculation is based on this geodesic, which is like a point-like approximation to the motion. At the same time, it's getting excited in this somewhat abstract sense that right. I think I understand what you're saying. Now, if it, were a situation where, well, just, okay, so since it's getting excited, that corresponds to it getting more massive. So the geodesic for, a massless and massive particle are different. And also, so, I mean, there are two questions. One is that, and also the fact that it's kind of spread out means, the question becomes, does that affect the geodesic or does it?
So you're asking, well, so I think that the choice of geodesic that we are using to connect 2 points is independent of the mass of the particle. For example, for the amplitude, it multiplies to it. I guess that, for example, there was so for example, so m is a mass of particle, and the amplitude is given by this formula for geodesic. And choice of L is independent of mass. It's sort of,
well, but the thing is, the mass is changing as you go, right? I mean, because you have the
yeah, that's right. So you start with this particular massive string state. So, and then as it travels, it becomes superposition of various different states. As they can all travel along the space like geodesic. Because geodesic equation is independent of mass.
So I think the effect that Eva is groping around is that as the state evolves, it becomes indeed a superposition of more massive states of the string. And now if you look at the Virasoro constraints, those tie the energy in the oscillator modes to the center of mass motion. And so as the string's getting more and more excited, the center of mass motion is now the motion for a massive geodesic. Oh, okay. And so it doesn't quite get out to the boundary. And I think this is what's causing the singularity to now roll off into something that's not singular, is that as more and more of the string is more and more massive, it can't quite get out to the boundary. And so there can't quite be a singularity in the Green's function.
I mean, in other words, even though it's a superposition, the expectation value of the energy density on the string or the number density after this particle production process is, is non-zero. So it's at that level, it's an excited string.
Okay. Yeah. Okay. I need to think whether the suppression due to this effect of particle getting mass affecting the trajectory is the same kind of effect as suppression I was talking about here, or different. It's not obvious to me they are the same.
So, okay. You guys are all saying they're the same. That would be interesting. I didn't realize that you were correcting the trajectory as the thing kind of time dependently got excited.
No, we are not doing that. Obviously.
So a massive particle can move on any geodesic, right? If you just boost it. So, I mean, the geodesic doesn't depend on the mass. It depends on the energy and the angular momentum.
But energy
The definition of energy and angular momentum get changed by this effect. So what the relation between the choice of geodesic and E and L can be modified. But you can still use the same geodesic, I think.
Yeah, I think. Yeah, I mean, one way to say it is that the solution, the zeroth order or the center of mass motion is a solution at all times to the equations of motion. So it doesn't get modified by the determinants. But I could be misunderstanding the question.
Well, I understand that it's space-like, so I shouldn't use real time of, you know, in terms of the single string, I shouldn't use real time intuition. But if I were to do that, then, you know, if you started with a light particle and just time dependently made it heavier, it would you know, go from being null to being time-like, for example. So the you know, in that situation, the trajectory would definitely be affected. I understand this is more abstract than that, and maybe somehow these two are the same. Email is quicker about identifying them.
I happen to know what's going on because Nick Warner and I have been doing a very similar calculation in fuzzball solutions.
Oh, okay.
One comment, I think that the suppression that Hiroshi was talking about is not related to the mass increasing. It's just because it ends up being a different state, right, which is orthogonal to the string state that you're trying to annihilate with the operator on the other side of the boundary.
That's correct.
So that's the reason, and so the two things you guys are talking about are not the same.
Yeah, that's what I would have guessed too. Thank you, Douglas. So I'm still.
Well, Eva, I think you were worried about the fact that as the string becomes excited, then this linearized analysis of the mode excitation could no longer be valid. But,
well, it's going over a quote unquote long time. So there's you know, what happens to the center of mass, you know, geodesic that's being used, and then there's also questions about the effect of the fact that it's also spreading out. But I was just now worrying about the fact that the geodesic itself would be adjusted.
I think it probably doesn't affect their. I think these considerations might be valid, but that shouldn't affect the answer too much, because the small tail of the correlator that is non-zero is coming from the part where like no oscillator excitation happens. And I think that their formulas are accurately computing the amplitude for no oscillator excitation to happen, even if the picture of the actual state that you get most of the time is not accurate.
Right, but doesn't enough of the state need to remain in order for you to pick up the singularity?
Well, so the amount of the state.
If there's very little of the state that remains in the massless mode, then there's no reason for there to be a singularity.
Yeah, that's the point of this talk.
Exactly.
So yeah, what you're saying, Douglas, is yeah, the geodesic of the massive stuff will adjust, but who cares, because it's not contributing to this. So that's
the exponential suppression they get is just from like many different modes, each of which could get excited, or roughly up to the energy p, and so you have an e to the minus p from them, and the part of the yeah,
that's right, that's true. I agree.
And so they only need to study what happens to the string when it's basically unexcited, and
right,
and the probability that continues to be unexcited.
Right. So they need to show that that is small, but that's what they do.
But yeah, that's where they're calculating. That's what they did.
Yeah, that's what we wanted to show. Yes.
So does the flux not matter? I mean, if you're literally doing some ADS CFT system, I mean, Emil, you would be dealing with all the stuff in some fuzzball solution.
So you're worried about the interaction of flux with string worksheet?
Yeah, I'm just asking how that enters in. I mean, there's for Ramon fluxes, there'd be some fermions that are involved, and maybe those don't get excited because the flux is so homogeneous or something.
Yeah, well, it may depend on what kind of initial state you choose, but perturbative string states are not charged with respect to Ramon flux. So,
no, they're not, but the world sheet has some fermion content associated with flux background being there. So
yeah, so
it's not that
Yeah,
they're.
so it can lead to excitations of the fermions on the world sheet. Yes.
Okay, thanks. That makes sense.
All right, if there are no further questions, let's thank Hiroshi again.
thank you.
See you guys next week.
Okay, thank you so much.
Thank you.
Bye-bye.
Bye-bye.